I'll use some kind of generic arguments that you kind of pick up as you're starting to program with these things and all of those kind of quirks of doing these things. Then I'll go directly into the workflow that you typically would encounter in a high-energy physics simulation pipeline or workflow. And then I'll talk about how we actually implement this inside of the Orchestral AI orchestration engine, and maybe look at an example conversation. We might do a live, we might not. We'll see. And then I'll end with some conclusions about where we want to go in the future. Right, so what are large language models? This is my favorite depiction of a large language model at some level. Typically when you interact with these things, you have some nice user-facing, friendly interactive mode. You can write to them, they're an oracle, you write to them, they stream back to your response, and then they stop. But behind that, of course, are these giant matrices, which Alex briefly showed, which is kind of this thing that is uninterpretable in a way that humans really just don't understand. Oh.
Don't whack the TV with it.
Yeah. Yeah, so you have this giant monster, but of course, in practice, these are just large matrices with some well-known architectures at this point. And really, the whole point of these large language models is that they're trying to learn this conditional probability distribution, where essentially it's just trying to predict the next tokens based on all previous context. So at some level, you have this giant string of text that you fed this thing, and its job is to, based on all of the previous text, predict the next token and do this until it perceives basically a stop token. And so this probability distribution in and of itself is extremely complicated and very hard to interpret at a human level. And it's basically using these giant models with billions and billions of parameters and then using the magic of gradient descent to learn the correlations that are basically inside of natural language itself. And so then what is an agent? So Alex gave a definition which is much more on the reinforcement side. In my context, it can all be mapped on together, but I'll consider an agent as something or a system which implements a conditional distribution over a particular set of actions that you can give this thing. And it's all going to be given that you initially have some context and you're at some decision steps. So you're at some point in your conversation, for example. And really importantly, as Alex was pointing out, is that it's really important that this thing is embedded in some type of feedback loop such that the previous actions then influence future decisions or future probability distributions of the tokens that get output. And so that's just the generic definition of an agent. What is the definition in the context of a large language model or a transformer-based agent? And really, when you go from tokens to actions, the only thing that changes is that now you're looking at a random variable, which is an action. So what is an action? An action would be something like a tool call, for example. So that is it's not necessarily a token, but it's an action that the system can take, and it can be, it can access these particular actions. And it's really a random variable over sets of tokens or sequences. And so really you transform this original kind of conditional probability distribution that the transformer is into a more kind of composite probability distribution over actions given some initial context, right? And so this is just some fancy way of saying you need to sum over all of the possible sequences of tokens that give you the same action, for example. And so this is a very abstract way of doing this, but in principle and conceptually, you can probably agree and see why this is the case. Right, and so this brings us to the question of, well, the question that I had initially when we started doing these things was, why is it useful to have tools, or why is it useful to kind of impart context? And the more, fundamentally, it's a new programming paradigm at some level. So it's, usual computer programming, you sit down, you write some code that executes predictably. When you're doing coding with agents, it's more of you're kind of probing a probability distribution that is the actual agent itself, or the LLM itself. And the game is, how do you get this agent to reliably perform as you would want it to at some level? And so intrinsically, given some context or some initial context, there are these actions that you want this LLM to perform, and inherently, this is going to have some uncertainty. So I'll give it a piece of text, I'm asking it to do something, and the question is, how reliable is the response to that piece of text? Right, and so generically, this uncertainty can kind of be broken down into two pieces. The first piece is kind of the uncertainty related to the task itself. So I've given it a task, and maybe that task is extremely broad or loose. Say I tell it to perform an action. If I were to, I literally type perform an action. The LLM will respond to me. If I repeat that action, the responses will wildly explode at some level. There's no real constraints on that particular type of prompt. And so there's an inherent uncertainty in the prompt that you actually, the task that you actually give this thing. The second source of uncertainty is how complicated is it to actually do that task that I've given it. So say I tell it to write a book that is a multi-part series on the history of seagulls or something. That inherently is going to be a very complicated task. It needs to research seagulls, it needs to then write, it needs to structure an outline for a book, and then needs to write the entire thing. So implicitly, this can also be a very large source of uncertainty, or it'll become more concrete when we talk about HEP pipelines. So generically, I've come up with this kind of structural diagram here. So this is representing the context length, or an arbitrary kind of timeline of context. The uncertainty I'll replicate, or I'll kind of say, or kind of denote like this, and then this initial L is kind of the initial conversation length that you may have. And so the question is, how do I reduce these particular types of uncertainty? Well, of course, the task uncertainty can just be reduced by giving relevant context. So if I tell it a very specific way of doing something, the uncertainty of the output is going to be much smaller at some level, right? And so you can see that this particular type of uncertainty actually has an associated scale in the dimension of context. You can get to a certain amount of context, relevant context, that eventually gets you to a point where this uncertainty is essentially zero. I can basically program, if I'm really good at prompt engineering, I can at some point get this uncertainty down to almost zero. I can have it almost always execute what I want it to, at least implement the task at some level as accurately as it can. The other uncertainty related to the execution can be reduced with tools. So if I provide it with some tools, it can greatly reduce the inherent kind of complications of trying to actually implement this particular type of task that you ask it to do. In the case of, so a good example of this would be, what's the difference? Say I didn't provide it tools, and I asked it to write a program which did some operation. If that task or that program is sufficiently large, it has to produce a lot of text in the form of code in order to implement this. Whereas if I write a tool which does the same task, all it has to do is then call that function or tool that I've created, and then it can just do the task without thinking about it or writing that code. Of course, there are kind of more fundamental uncertainties related to these things. So there's always going to be a baseline level of noise in the reasoning of these large language models. So fundamentally, there's going to be eventually, depending on how good the model is, there's always some base layer of kind of statistical noise, which you're never going to be able to get below. In practice, in modern models, this type of error is not actually such a big deal, I don't think. What is much more relevant is kind of dilution of context, basically. So as you start with the conversation, the more and more context you provide, the worse and worse that the agent or LLM is going to remember the previous bits of this particular thing. And it's not really known right now how this scales as a function. It's really a modeling type of thing that needs to be considered. And so context, it kind of introduces, again, more scales into this context problem where you need to be conscious of, if I make my context too long, this thing is actually not going to be able to do what I'm asking it to because it doesn't remember all the way back at the beginning of the conversation when I said, never report the number 2 or something like this.
Why can't you just feed that back in?
You can, of course. But you have to, you don't know what it doesn't know. You know what I mean? So like this is an empirical thing. You'd have to see, for a particular model, you'd have to come up with some tests that gives you some notion of what's the context length of this particular LLM. And then from there you can know, oh, if I go over this context, maybe I should remind it of what to do. Or you can also, there are ways and methods of compactifying these conversations into a more like a summary of the previous conversation. That's probably the best way to do it. You just compactify and summarize after you reach a certain limit. And so in practice, what are we actually doing here? What's the reason for going through all of this? In practice, you're really only interested in getting this thing to be reliable up to a certain point. So you're happy with maybe a 95% success rate on a particular task that you give it for a particular type of prompt. And so the game then is, when you're doing this programming, it's how much context do I need to feed into this thing such that my context error is smaller than my my tool error or my execution error and my implicit task error. And this is where higher energy physics workflows kind of go into this. It's a sufficiently complicated task where it needs a good amount of context in order to understand what you want it to do, and it also needs a bunch of tools to also facilitate and enable you to do this type of task. So what's the task? So you can consider some typical BSM models. So you have a scalar leptoquark. You couple this thing, you limit the couplings in this simple scenario to interacting with, we'll do up quarks and electrons. And of course then the signature that you're trying to probe and look at, say at an experiment, would be PP to this kind of intermediate resonance, which would be this leptoquark, to a di-lepton jet system, basically. And then the game is, can I reconstruct these masses given the output events that I get? Right, and so typically how do you do this inside of a high energy physics kind of software pipeline? Typically, the way that you'd start to do this is you'd write a Lagrangian, of course, in the form of a model file for fine rules. You take this fine rule file, of course this will give you all the interactions of the model, etc., and package it into a nice UFO, a universal fine rules output, which can then has compatibility with MabGraph. So MabGraph is just a matrix element generator. And so you can feed that BSM model file into this MabGraph program. The program will spit out a bunch of partonic events, basically, for momenta. And then, since they're partonic events, you're going to need to shower and hadronize these things and basically propagate them down to a scale where you only have hadrons as the output. And of course, this can all be implemented with something like Pythia, Sherpa, or Herwig, if you want. At the end of the day, what do you get? You get some event record, which is essentially just a data structure which tells you what particles came out, what's their px, py, pz in energy, and a bunch of other potential metadata that might be relevant to the particular simulation that occurred. Right, and so that's kind of the pipeline, and the question is, now the task at hand is to have an agent do this, is to have some type of large language model try to implement this with the least amount of user interaction as possible, or with me prompting it to do these particular tasks. And that's where this HEP toolkit for agentic planning, orchestration, and deployment comes in. We call this HEPTAPOD. And it's, of course, built using this nice framework that these two gentlemen in the front made. And so it's basically just a giant toolkit for HEP-specific tasks, which essentially interfaces with fine rules, MabGraph, and Pythia, and other event generators in the future that allow it to do this and successfully implement this pipeline. And of course, there are some philosophical decisions. All of these programs essentially run with run cards. So a run card is just a program-specific syntax that you can feed into the program and it will execute the program in a particular way that they define. So this is particularly important because it makes this whole thing, at some level, it keeps a human in the loop, so that essentially the way that we're kind of imagining this thing being used is that you supply this thing with a bunch of run cards, or in the future, you can help you generate run cards. And then given that you put in the run cards, anything that this outputs, and this kind of comes back to the question that we had earlier of whether or not you can trust this thing, you can basically trust it then as much as you are able and kind of knowledgeable enough to write these run cards at some level. So garbage in, garbage out, and so it keeps this human in the loop type of thing and keeps each of these steps reviewable by human researchers. Of course, in order to kind of do these things, you need to have an LLM digestible kind of data structure for the events that come out. So you have these four momenta. You don't want to put these into a very compressed file structure that then needs to be parsed and deserialized and et cetera, et cetera, et cetera. So you have to we came up with a way to basically write out these events inside of a JSON list file type, which allows it to have explicit access to each of the events line by line, and you can interact with them in a predictable way. Of course, on top of all the tools that are written, you have to have prompts which kind of guide you towards where you need to go. And so it has, of course, task-specific context, prompting, and then, of course, when you get an error message, what's nice about the Orchestra framework is that if you get an error message, you can, essentially inject a particularly useful string that gets reported back to the agent so that it can think about the error that it just got in a natural language way, and then try to fix this thing. And it typically will help you kind of avoid these typical things where if you were writing a script, it would terminate the program, and then you have to go back to that line, you have to fix it, etc., etc. With the LLM, it will just fix it on the fly. Right, and so this is a generic diagram. It's extremely useful in the sense that it's detailed. It's not great for a 30-minute presentation to go through, but it really just summarizes how this thing works as a whole. Really, this middle piece is essentially just how the Orchestra framework works, more or less. And then these outer things, so as Alex was saying, all of this operates in a localized sandbox, so you can't do so. I tried to make this kind of look like a jail cell. The LLM agent is not able to get out of this at some level, so it can only put files, read and write files from this particular place, and that includes any tools that it executes, so it can only access this particularly guarded space. Of course, what's nice with the Orchestra framework is that you have this schema generation and validation for these LLMs to read and digest, making things less error prone. But essentially, the basic structure is you have the user, it puts in a prompt, it goes through this whole toolkit of going to the provider, getting a response, are there tool calls, run the tools, output the responses. And so really at the end of the day, what we can do is we can look at an example conversation. We could do a live, but it's just easier to do it this way. So what does a typical conversation look like? So this is the initial kind of directory structure that we provided with. There's a find rules directory, madgraph directory, and a Pythia directory. Each of these has the relevant run cards within them. We give it this nice, long, probably too long system prompt so that it just basically outlines what it needs to do and what is typical of a generic BSM workflow. And then we give it a user prompt in the sense that now that I typed this into the terminal. So plan a Monte Carlo signal validation analysis of the BSM scalar leptoquark defined by the supplied run cards, generate some events, apply some cuts, try to reproduce this invariant mass distribution essentially. And so this is in what I would call a planning type conversation. So the prompting is essentially telling the agent to very explicitly make a plan and execute the plan. And so you'll see that in some of these prompts. So the first thing it does, of course, is lists the directory. It sees what files it has, followed by writing a to-do list. So this is agent generated, this is LLM generated. It generated this nice to-do list, which is a nice feature that they built into this thing by default. And essentially it says, okay, I need to start with generating the UFO files, which it does. It calls the find rules tool. So it calls the find rules tool here, and then it reads the next madgraph file, which is nice. Then generates the events with madgraph, reads the next Pythia file, generates the events with Pythia. And so in this example, there are 3 mass parameters for the scalar leptoquark inside of madgraph, so it automatically handles all of that. So if you generate multiple parameter points, it automatically knows that these have been generated. Generates Pythia, does it for the other 2 particular parameter points. In order to do this analysis, you need to cluster these jets. So it clusters the jets, does it again, goes back to the to-do right, updates what it's already done, it goes to the next task. It then starts to do some analysis. It filters out some garbage that it doesn't need. It gets the highest PT leptons and jets in the system. It can reconstruct the resonance. So there's a class of essentially resonance reconstruction tools that I coded in that it can use to generate these resonances. It continues, filters, eventually, which is nice, is that it gets to a point where it tries to do the next resonance reconstruction, but it gets an error, a processing error, which is essentially telling it that it never clustered one of the parameter points. And so it tries to get the hardest of that particular thing. Actually, I need to actually cluster those events. So it then clusters, does now it can do the actual resonance reconstruction. And then the end of the game is basically to output this particular invariant mass distribution that we wanted in the first place. It summarizes what it did, and this is the final output. So you can see here clearly it's getting this giant resonance peak directly at these particular leptoquark masses. So it would seem that the signal's been validated, and so that's the end of the example. So that's typically what it goes by. And so just to end here, I think almost on time, is the conclusion. So, right, HEPTAPOD, it's a soon-to-be live thing, so this paper is it's ready to go out. We're just waiting on some confirmation and permission. In the future work, we're looking to, of course, as I kind of mentioned, develop a way to really help people write these run cards because it can be kind of finicky at some level. There's, of course, way more applications that you can do inside of a high-energy physics context where this becomes even more useful. And then, as Alex mentioned, probably we'll start playing with some type of agentic herding or using multiple agents at the same time to kind of do these things. Thanks for your attention.
Now you can ask questions about the physics.
Yes, please.
In the back.
So, Alex mentioned the tools, and now you're mentioning the run cards. Are the run cards basically wrappers around the tools, or are they two different things?
Run cards?
Yeah.
Yeah, those are completely separate. So those are input into these programs, basically. So high energy physics, you have MadGraph, you have Pythia, you have this XYZ. Each of these can take input as in the form of a run card, which is essentially just I can show you an example.
So some kind of like JSON thing.
It's just a text file, basically,
Yeah, okay.
which has some very specific syntax, which then each of these programs has a dedicated parser, which then basically extracts the relevant parameters for the program to run, and then it feeds it directly into the program.
It's just a way for you to provide more information for it.
Yeah, exactly. It's a way to run it without having to. Really, the use is that you don't have to interact with the program at all. Say I wanted to generate a bunch of events, but I didn't want to do it through the terminal. I could just feed it a run card, change the parameters a little bit, feed it back. It'll generate all the events. You don't have to. It's basically a nicety of these, and it works well when you're doing parallel event generation, et cetera, et cetera.
In practice, it's implemented as his tools accept a path to the run card.
Yeah, exactly.
Yes. So
Yes.
it's not a tool. It's a file.
Yeah. It's a file that then is fed as an argument. The path of that file is fed as an argument to the tools such that the programs know where it
And
is.
presumably, since this is built on Orchestral AI, you can still write tools for this for the HAP box as well.
Yes. Yes. So, what do you mean exactly?
Well, the interface of writing, if you want to do something that isn't implemented here, you can still extend it with your own tool, or did you?
Yes,
write
of course,
that
of course, of course.
Yeah.
So this is a generic list of tools that help you generate events. You can do almost anything off of that. Now, of course, if you're interested in generating events, then these tools are what are going to be useful for you. I mean, that's the main purpose of these programs in the first place. But yeah, you can implement different. What's nice is that now I can write any run card that I want. If it's a valid run card, I can use these tools to then use those run cards to generate events. I don't have to rewrite these tools in order to generate different types of events, for example.
So coming back to your execution uncertainty, can't you run the agent 1,000 times and validate how often it gets it right and how?
Yeah, absolutely. So
You
it's.
haven't done it?
I've not done it yet, so it's completely empirical thing. You definitely do have to run it. So these tests will be done in the future, of course. And each model that you use, so there's a whole zoo of models that you can use. Each of these models will most likely have a different performance on a particular metric.
More difficult ones.
Exactly. So the smarter models might do a little bit better. And of course, it's all a function of the prompting itself. So if you fix the prompting and you fix the task, then you can write these empirical validation tests, or and try to get some understanding of how uncertain is this particular LLM at doing this particular task.
But also don't forget that every time you run it, you have to pay. So if you're going
Yeah,
to run
yeah.
it 1,000 times, you
Yeah,
have to
yeah,
pay 1,000 times.
Yeah.
That's the agent that makes free
I believe-
subscriptions.
Yeah, the question here.
Yes.
Yes.
Most AIs that I've had experience with, they seem to struggle a lot with even drawing simple like Feynman diagrams.
Mhm.
Can this framework reliably draw Feynman diagrams?
It cannot. So you could write a tool to write them. Now, of course, when you generate events with MadGraph, it outputs a Feynman diagram for you. So this tool, a feature that will be added to this MadGraph tool is, for example, show me the Feynman diagram of this process that I just generated, for example. But of course, you could also write a tool that equivalently writes and generates Feynman diagrams, given some, input, some specific syntax. So you could use. There are these nice packages which operate based off of a certain syntax. I forget what it's called. It's metafont based. I forget what it's called, but you could use that and write a tool to write programs which will then give you out particular Feynman diagrams. Yeah.
Yes.
I'm still trying to find out how to ask my question,
Yeah.
which I think is just going to take a long, long time. And probably I don't understand the stuff in some sense.
I'd love to hear
So
your
for
views.
example, batch processing, I mean, I don't know, it's just like you've written a whole bunch of code to do stuff and then you tell me now I can just ask the model to do it. Great, but you have to write that code. Why not just give me the code? I run a batch processing or something and do it
Oh,
myself.
so like, why not just write a script? to do all of this?
Where are we going? That's my question maybe. How is this different? Because all this stuff y'all are doing on the back end, you could just give me the back end and I could put in my own, instead of trying to give context to a thing that I don't know what's going to do, I could actually put in exact context.
Right. So this is almost, you could think of this as a proof of context that this can do this task at some level. In the future, you can imagine, just like you interact with a graduate student, you come up with a problem, you say, oh, maybe this is an interesting signature to look at. Now grad student, go and do this particular thing, and typically that will involve, this is the simplest case, but typically that will involve looking at a scan of parameters, which you basically have to choose by hand. You have to run the code a bunch. This, given particular prompting, can automate all of that, such that a grad student in principle doesn't have to, I don't want to say it's replacing a grad student, but say you're a professional researcher, you could do this without ever having a graduate student. So at some level, it lowers the bar of, it can increase your output if you'd like, or, but for particular tasks where you're just generating events, scripting is probably okay. If you're trying to do more exploratory things where you're trying to interact with, where you're saying, choose a particular set of parameters which might be useful for this particular signal. I want to see this signal. What is the branching, or what is the cross-section that I need in order to see this signal? That's the kind of stuff that this can eventually do. This is really just the kind of the lower floor. If it couldn't do this, there's no way to go from there at some level.
And how is it, or it's going to somehow maybe have more context than say some sort of Monte Carlo where I just say, hey, just choose some random things. I can run that
Absolutely.
really cheap.
So
running something
you'll know. So one thing I didn't point out is that when it clustered those events, when you cluster jets, you need these parameters. So you need the minimum PT of the jet. You need the jet radius. It just chose those. I didn't tell it what those were. It just chose some values which actually end up being like what you would choose. So it has implicit context based off of its memory from what it's been trained on, basically. It knows that, oh, maybe I need a jet radius of 0.8, whatever, blah, 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 blah. So that's all baked in there, and it kind of knows that stuff for free. Now, of course, depending on what you're doing, you can tell explicitly what to do. The sky is the limit. It's really, you can do almost anything you can think of at some level.
But that would be faster than Monte Carlo?
So this still, so what do you mean by that? So this still does, so this still has to generate it. So it still generates, so there's still a time sync of, if I ask it to generate 1 million events, it still has to generate those 1 million events. It might reduce your time to the correct events. Typically you iterate, like you generate events, they're garbage, generate again, generate again, generate again, until you finally get something out that is what you actually want. This could kind of minimize that process at some level. Just like Google, it's at some level you could think in particular tasks, it's a more informed Google. If you ask Google, how do I generate events for this particular VSM signature, it's not going to be able to do anything for you, whereas this, in principle, could. There's many use cases.
I mean, it's true that you can write a script, but let me ask you this. Are you going to sit down and write the script, or are you going to ask your graduate student to do it?
Well, I guess the
Probably
question
the
is
latter.
why didn't he just provide me the
And-
script he wrote instead of this front end that has AI in it?
So he hasn't.
It's
sorry,
much
Jake.
more
He
flexible.
hasn't written just a script, right? He's written the elements that can be put together to make that script, but they could also be put together to make many other scripts.
Okay,
What were you
so
gonna say?
that's maybe that's the pieces. So
Yeah.
all these pieces could be put together multiple ways instead of just.
Yeah, they're like
Exactly.
Yes.
think of
That's
them like
super
building
flexible.
blocks. Yeah.
Yeah,
I
super,
think-
super flexible.
I think the goal is increased versatility over a script. It's like an agent
Yeah.
sitting in a lab full of toys it can play with
Yes,
to try and
exactly.
find something novel.
Yeah, maybe more context for
Yeah,
science
again-
because I mean this sounds like functions I would call for a programming.
Yeah,
You know,
yeah.
like if I got
Yeah.
Python, I can call functions. I don't have to write the scripts anymore.
But
Exactly, yeah.
implicitly, if you write a
abstraction.
script, that script is for a single analysis. This, you can just, if you have the run cards, you can just feed the run cards to this and it'll generate all of those things. You don't have to do this metadata analysis of changing the paths. This handles all of the paths. You don't have to worry about the paths at all. It writes the paths, remembers the paths that it's written out. Knows where the data is stored. It can analyze the data that's stored, convert the data format to all of these things.
It can automatically correct errors that occur.
It can automatically correct errors. If you write a script, you have a bug somewhere in the middle of the file, it terminates the program. This would return an error. The LLM can fix that error in the script and then continue running from there.
This is simply scratching the surface. There's a
Yes,
lot
yes,
more
yes.
opportunities and functionalities that are
And things that we
available.
probably haven't even thought about, which are. gonna
And
be
we
useful.
would love to chat with all of you during the coffee break. And now we need to move on and stay on schedule. Thank you, Tony.
Yes.
Thank you.